Hi, my name is Wenjin Chu. This is going to be a presentation about reference architecture for trust over the internet. Let me share the screen with you. And this talk was first given April 26th in the Internet Identity Workshop back in April in Mountain View. And it's now being recorded for the benefit of those who couldn't attend in person. So what we're trying to do, the background here is that it is a new organization, Trust over IP, who proposed a dual stack on how to implement trust or introduce trust support over the internet. And the stack is shown on the left, which shows two columns, one on technology or protocols, and on the right side about governance or how you may operate and administer such a system. That both sides are needed. My talk is mostly going to be focused on the left side on technology, but it will have a lot of implications and influences over the right side as well. So we'll see as we come to those. This stack is commonly expressed as different layers, from layer 1 about utilities, layer 2 on peer-to-peer communication, layer 3 different kinds of trust tasks, and layer 4 applications you may be able to build based on the lower layer functionalities. And this diagram or this view is not very precise. And so there's a need for a more precise architecture for developers, for technical product managers, and or to discuss different choices we may have, etc. And so this is really beneficial, and that's my topic today. A reference architecture that we will come back and probably link to this graphical diagram on the left again later. Let's start with what is a stack. It's been used quite liberally nowadays, but a stack to me is to view the decomposition of complex functionalities in a vertical way, where each higher layer incrementally adds functionality above the layers below it. It is suitable within a particular domain where dependencies are clearly ordered, but it's not as suitable to capture relationships between domains. And I believe the reference architecture is a prerequisite to understand a stack. What do I mean by that? Well, I'm going to show some analogy with a picture of downtown San Francisco here. And so layers of a stack in software within a particular domain or particular function we want to implement looks like a tall building. And you have many, many layers. And let's say that the higher layers have dependency on lower layers. But it's not just one building. So in a complex ecosystem, you have many buildings representing different parties who communicate with each other collaboratively to implement more sophisticated, more complex functionalities. And so between these buildings, we will have what we call protocols. And these protocols operate in certain layer. So when we speak of a protocol, we need to be aware which layer we're speaking of. And so collectively, this picture with multiple stacks and how they interact with each other constitutes what I mean by a reference architecture. So that's a good analogy, but still quite fuzzy. So let's take some examples. Hopefully most people understand what is an internet architecture, and it's often expressed as a stack. People call that TCP/IP stack, picking on two of the most commonly known protocols in that stack. But more specifically, if you look at on the left side here, the internet protocol stack really starts with the physical and link layer, where different kinds of physical networks. This picture is a little bit old, but a very common network physical, the link layer, that's the term, or layer 2. There are Ethernet or Wi-Fi, and your broadband at home, or wireless nowadays. And the internet layer then in layer 3 make an abstraction of these lower layers, and therefore you have one single layer have a commonality of what we know as the internet. And the protocols above that then provide more specific functionalities depend on the application's needs. And these functionalities are also abstracted. The two most commonly known examples are TCP for connectionless and UDP for, TCP for connection-oriented and UDP for connectionless transport layers. And then applications such as emails, file transfer, and later on, I think more important to us now, HTTP for web. So these typically what people are referring to as a stack for the internet. The reference architecture for the internet are shown on the right side, which really laid down the landscape of what the internet look like. So in this case, you start with an endpoint, for example, a mobile phone or a laptop, which connects to the local network, eventually reach a router. And the router really is the node that we jump onto the true internet, which is with intradomain and interdomain protocols. So, intradomain protocol, for example, OSPF, interdomain routing protocol, such as BGP, who collectively populate different hierarchy of the internet infrastructure with the proper routing tables, which allows the packet we send from one node traverse sometimes through many hops over the internet, and eventually reach the destination. On the destination side, the exactly same thing happens. And so this allows a internet to be a scale to the enormous size we have today, and also ensure universal reachability. Anybody can send a packet to anybody else, as long as you are connected to the internet through these layers of protocols. Let's take another example more related to trust. So this is the OpenID Connect protocol. And the Connect protocol really, if you look at OIDC's specification in the very beginning, will show this diagram on the left. And in the diagram, really, it shows three parties here: an end user, relying party, RP, and the OP, or the OpenID provider. The provider the ID provider, the relying party will be, for example, your web service, and end user would be the web browser or the person who's using a web browser to access a web service. So for example, a merchant that you want to buy something from. And the OpenID provider is an entity who provides the authentication and the login in the end, right, for the user. I flipped this end user around on the right side to make the relationship, I think, more clear. So it's exactly identical, but we put the end user on one side and relying party on the left, and the OpenID provider in the middle. And you can see the relationship between them. The ID provider is a central entity that is a required entity and also knows most of the information flow, as you can see, for the authentication. While at end user, a relying party are the two sides of the two parties who really want to talk to each other. So in this solution, we rely on the central entity to provide the authentication or trust that the relying party and end user needed. And because the relying party and end user are like two strangers, they don't know each other initially, and you need some way to bridge that trust. So this is a very good way of also showing the reference architecture. This is another example showing why the reference architecture is so important, because it makes that the relationship very clear and easy to understand. Now, the Trust over IP Foundation, the community had numerous discussions, and we come to some goals we want to achieve. And these goals I've summarized here. They, as I mentioned, the first one would be a universal connectivity. The second one is related to the architecture, how it's going to work. So it's named as an hourglass. I'll come to that later. End-to-end simply means that most of the features reside in the end systems. Basically, the devices and laptops we own, rather than in middle of the network. Decentralization, we just sort of hinted at, but it is about who have the control really. And decentralization just trying to avoid centralizing all the information on all the control in one party. Verifiability or authenticity, and then basically knowing who we're talking to, and that's the basis of trust. The fundamental starting point of it. And confidentiality involved about the information, how we share information, or information be kept within the two party talking to without any third party knowing about it. And similarly, privacy means who has control of my one party's information, what you can disclose, what you don't have to disclose. And the hourglass really comes down to this particular picture I want to probably come back to in several occasions. We talked about the IP or internet protocol for the internet as the improbability layer. I means internet networking. So if you look at it below the IP layer, there are numerous different ways you can implement or you can realize a network, right? From Ethernet to Wi-Fi, etc. Above the IP layer, you can have all kinds of different protocols designed for long-term connections, short-term messaging, and which also supports numerous different kind of applications. So both require, I think, optimization and diversity. We want more and more ways and make them cheaper and cheaper and more feature-rich. But we also want interoperability or universal interoperability, meaning that anyone can send something to anybody else. And that is achieved by this very minimalistic internet protocol. That's why we call it spanning layer, because it's universally reachable, but also it's a narrow, meaning that it has very little functionality in it, as little as possible. And so this gives us a shape, look like a hourglass. In order to achieve trust while still keep the benefit of the internet as a universally reachable network, we want to adopt the same mechanism. Basically, we want to also provide a trust spanning layer, similar to IP as a reachability spanning layer, you can say, and which is on top of the internet, what we have today, but also with this minimum functionality needed in order to achieve the interoperability and reachability with trust, right? The new function we're adding to is the trust. And so let's jump on to the reference architecture we are proposing. So in this case, we are overlaying everything on top of the existing internet. No new functionality are really needed from the internet itself. We want to, any end system A, be able to reach any end system B, but with full trust. So in order to achieve this, all the subsystems shown here are delineated by the locus of control, or sometimes people call it domain. Because if one have no control over a particular system or a device, we really cannot control, we really cannot trust. So the locus of control has to be the basis as we define these systems. If we want to be able to confidently reason about trust and relate to that risk or distrust of any device or system and the person behind it, right? So these systems then interact through a set of protocols, not just one protocol, but really a set of them here. And we've talked about the end system to end system protocol. That's the one right in the middle. The end system cannot really achieve this easily just by themselves. And so we always need some kind of support system that's not local here. So for instance, if today we tend to provide a database, for example, with who can attest who I am, my name, my email address, etc. And that will be a support system. It's not under my control, but I have dependencies on these systems. They're not necessary for communication from a system A to system B, but they are necessary for attesting or supporting the system A be able to prove it is A. And so those are the supporting systems. Intermediary systems are also sometimes very beneficial or needed. They do forwarding for the end systems. So they are actually in the data path, but they are not a dependency on proving who I am. Okay, so I'm trying to, we'll come to define these more precisely later. And the key thing to understand here that each type of system has a shared stack, right? So an end system and two end systems, they should have some shared stack architecture, but they are not, the stack are not the same between a end system and a support system, or an end system and an intermediary system. So in this architecture, there's a very important protocol that's end system to end system, or peer-to-peer, right? This is the trust spanning layer we're going to come to. So we just talk about, this is the layer that talking about the trust spanning layer. This is the between two end systems. And the end systems may actually need to access some supporting systems. The examples of supporting system can be, data registries, VDRs, for example, witness and watchers in the carry design. It can be for accounting and auditing purposes. It can be a reputation system, which also provides some kind of identity service. It can be discovery systems for searching who I want to talk to, for example. All these are examples of supporting systems. The intermediary systems also can do message forwarding functions. They can also do anonymity, for example, or holding messages on behalf of users for future delivery. And it can also play the role of helping one person with multiple devices and be able to ensure that you send a message and that can be delivered to you no matter which device that you're on, for instance, right? That's a delivery service. So all these intermediary systems and supporting systems, they're not mandatory, but very, very useful. And in a practical system, they are often quite important. Let's look at on end systems, specifically on the end systems. And this is where is defined by locus of control. And the end system, we look at a 4-layer pattern of functionalities. And again, the layer 2 is the one that involves trust spanning, or this is really the interconnectivity layer. Okay, and so layer 2 is special in the sense that we really want to arrive at one single layer 2. It can be extremely simple and thin, but it has to be universal in order for higher layer interoperability and also the freedom of implementation in the layer 1. For clarity, mostly just so that we can avoid the overlap of terminologies, we want to call the interaction between layers interfaces and interaction between two end systems protocols. So those are typically remote, right? Even though the interfaces sometimes could be remote as well, and we'll come to that. But conceptually, you should look at the end system as a piece of, commonly as a piece of a physical equipment, but also can be implemented in the larger system as long as you can maintain the locus of control. Here again, let's compare this particular stack with the TCP IP and hourglass we just shown earlier. And so the layer 1, because our layer 1 is really the internet itself. You can think of the whatever communication services available in the internet as layer 1, and layer 2 is where the trust spanning layer is going to be, and 3 and 4 are higher layers. So 3 is more of a component trust tasks, reusable things, similar to TCP and UDP, and layer 4 are truly applications. So how the layer 2 and layer 1 relate to each other? Again, our definition of all the layers start with layer 2. So layer 2, what layer 2 need to do? again, very similar to what Internet Protocol does. What does it do? You need addressing and need some kind of messaging. Just two things, really. And the addressing we are referring to can be a DID, decentralized ID, or AID as autonomic identifier in carry. Both are good examples of a addressing in layer 2. And a end-to-end verifiable messaging protocol is simply a way for any two DIDs be able to send a message from A to B. And in order to realize that, we need a address resolution. So from layer 2, the DID we need to look up so that we translate a DID into some address the lower layer transport protocol can use. So if it's a HTTP, that will be your URL. If it's a IP layer, it will be IP address, for example. Right? So everything eventually reach to a addressing that is available on the internet. And from there, it can be delivered on the other side to the end system B. And end system B then need to be able to deliver up the stack to the resolved party. Essentially, that would be the DID B, right? And the difference, I think, in the trust spanning protocol or the layer 2 is the proper trust properties. And the 3 properties we really want to highlight is A, authenticity. That's really the most important one. And then optionally, but often needed, is confidentiality. And then optional, but often needed, is privacy. And so these are the basic layers allowed to end systems and to achieve the minimum functionality needed. And any less would not be able to support all the trust applications we wanted to support. So this is the fundamental building blocks that all of us are going to need. And it's simple enough that I can implement it in almost all any devices simply by using what is available on the internet. Let's now move on to supporting systems. And the best way to look at it is taking some examples. So the first example we can look at it is based on Indy and Aris. Indy as a blockchain implementation and Aris as an API to sort of use those and also implement verifiable credentials in the client software. Okay, so if we look at the end system, and this is four layers. Supposedly, you will be, a application developer will be thinking about layer 4. That can be, you may be thinking about digital wallet with identifiers or credentials, maybe for payment. Those are your applications. While layer 3 gives some reusable pattern. So in Indy, there will be anon class. Is a type of credentials, and also maybe some protocol to reach the ledger or the identifier to prove, for example, or verify who you are using Indy service. In layer 2, really, it's the DID Indy. And so that's the DID layer, resolve that DID layer, and come back. And that requires quite a bit of a library to implement that as well, primarily on the pool service. So the pool is really the DID Indy ID management, right? And then the name and replace keys are really key manager or key manager in the DKMI. So those are the key functionality that allow layer 2 to function. You do that, implement that, or layer 2 implement that through API to a supporting system, and that supporting system is one of the indie services. In layer 1, you need a labor indie wallet. So wallet provide key materials and also a secure install of those secrets. Another part of layer 1 is HTTPS, and over the web, over the internet, essentially give you a transport service. Now this transport service can be multiple choices, and any areas certainly allow various kinds of different services on there as well. And in theory, this can be any transport service, in fact, it can go beyond even internet. It can be based on a network that is outside of the typical internet architecture as well. But layer 1's needs are very clear. Essentially, really, it comes down to key material, secure store, and some kind of a transport service that can reach everybody that you want to reach. The second example I'm going to showcase here is Carry. So Carry provides another type of supporting system, and this supporting system consists of quite a bit of things, and I'm showing here in the diagram a witness. Now, all these supporting systems might be optional in very strict and special cases, but most of for common applications, I think these are actually required. So a witness, for example, a witness allows the functionality of key management, essentially. And in the rest of the application and the pattern look very similar. And I think the key difference is that in this case, layer 2 implements a carry witness protocol, while the interface to layer 1 still consists of a key material, secure store, like for example, key event lock need to be implemented securely in the end systems storage. And similarly, the transport layer can be anything. It will be HTTPS, but can certainly use other transport layer protocols, even purely connectionless protocols as well. The carry uses supporting systems such as watchers, in addition to witness pool, and all of these examples, and there are maybe many such supporting systems to fully deploy a carry system, and these are all examples of supporting systems. These belong to, so as long as such a service requires the functioning of the AID, the authenticity of AID and the base layer end-to-end communication requirements belong to layer 2. And so the layer 2 functionality, if you compare the two, are actually quite similar. The precise nature of the protocol may be different, but the pattern looks very much the same. And the functionality we want to achieve look very much similar as well in the general sense. So we can go on with some more examples, but I would like to basically summarize and show this particular generalized reference architecture example. In this architecture example, you have system A and system B, two end systems, each with 4 layers. The layer 1, 3, and 4 can all be quite different for both of them. But layer 2 are identical. So this is the trust spanning layer, and 3 and 4 applications, if they happen to be in a particular application, they will share those components as well. But if they are not, then those layers can be all different. And each one of them can have multiple instances of it, right? Depending on which application you're running. And each end system, in order to sort of get the trust basis support, needs some kind of support service. And so that support service is provided by various support systems for end system A, and end system B could have entirely, totally unrelated support services based on, you can get that service from different vendors or different systems or different methods, and all that are valid and makes the whole system work. And with the functionality, the trust functionality we need, but also the universal reachability and interoperability maintained throughout a rich ecosystem. The last topic I want to address is intermediary systems. So here's one example of intermediary system using DITCOM v2. In DITCOM v2, there's a mediator as the example of an intermediary system. So mediator does message forwarding by wrapping, I think, one message around with another layer of encapsulation. So in this example, these intermediary systems talk to end system A based on the trust spanning protocol as a way to deliver the message. That message can be then forwarded to one or more intermediary systems, so very similar to how router routes IP packets, but it's in the trust layer, right? In the layer above the transport layer. And eventually that can be then delivered to end system B. Could it be many hops away? And could it be quite different kind of an intermediary system when you face system B? So the two end systems can have different choices. Again, of who, which vendor or which system you want to choose as intermediary, but they can still interoperable. So so we allow maximum flexibility on who do we trust and what kind of service we want to rely on. But the service, the mediators in this case, do not, they are not part of our trust system. So we don't have to rely on them for trust. We don't rely on them for keeping our private information. And all they're doing is simply passing messaging around. So their goal, their job is to deliver the message for us with high throughput, low latency, scalability, low cost, right? And they can optimize all those without us having to be trust the entire complex system unconditionally, right? We always have some dependency on them, like for example, availability, whether the service is up and down. But fundamentally, we no longer see intermediary systems as the trust base, as part of the trust base. So that's very important to keep in mind. Then we can choose this system based on their performance and reliability, etc., but not on how we want to keep private data and trust relationships. Here is another example. This one was added later. I thought it would add here. It wasn't there in the initial IW presentation, but this is the decentralized web node, or DWN. sometimes called decentralized web platform. They are essentially very similar thing that based on IPFS and IPFS replication. So the intermediary node system in this case is this DWN, right? I'm showing here as 3 different systems, and they really don't need to know anything about the 2N systems. 2N system can utilize their functionality, but does not have to have reliability, dependency on them for trust and trust relationships. So in this case, it's outside of the DWN scope on the, at least in this layer, okay, on the identity and authenticity of N system A and B, but they provide a IPFS-based transport mechanism, and that can be replicated between them so that the N system A and N system B may be talking to very different kinds of a node, DWN nodes, but the message will be reached with the same trust guarantees that system A and B have in mind, and using the same trust spanning protocol in layer 2. Okay, so if you have 2 DIDs, you have some kind of a IPFS API for transport, and the DWN system will, replicate these and eventually deliver the message to N system B based on DID B and DID A 2 addresses only. So this is the perfect example of how the trust spanning protocol allow various kinds of implementations and provide end-to-end communication with trust guarantees, and your trust relationship, they stay with you. So let me put all this together into a little bit on how a N systems protocol stack would work. So here's the protocol stack as we've shown before. And we look at the layer 2. Layer 2 rely on something interface to layer 1 in order to support, in order to have the crypto, the key materials for the protocol, and also secure storage for secrets and transport over the internet. In addition, the layer 2 needs, 0, 1, or more to access to support systems, so that these support systems allow layer 2 to be able to prove the authenticity. In addition, the layer 2 needs to implement a trust spanning protocol, and that's the main part is to using a support system to implement a DID, and then implement the functionality required in the trust spanning protocol, and do that purely based on the interface to layer 1 only, and shouldn't really need anything else. So that really gives the foundation. These 3 things give you the foundation of a trust spanning protocol that gives you the trust guarantees and maintain internet-wide end-to-end reachability. We talked about it a bit earlier, but I just want to mention again that layer 1 in theory could be also remote. Conceptually, it's still the same layer 1, by offloading some of the cloud or wallet services into the cloud, wallet services to the cloud. So if we choose to do that, it's conceptually still within layer 1, but this implementation need to have another mean to guarantee that you can still be, it is under your locus of control, right? It's still as trustworthy as if under your own control. So that is the requirement if we ever want to offload layer 1 to a cloud or remote service that way. But conceptually that can be done. Okay, so that's it, what I want to cover. In the IRW presentation, there's a lot of discussions, but for this recording, we will stay with a simple presentation. So with this reference architecture, the details of each layer, the interfaces, protocols, then they can be specified one by one, which taken as a whole completes the technical specification. Then you have the entire stack for implementation. What I have done here is just present how we go do that and why we should do it this way. And that's why it's a reference architecture. It gives you a big picture of what each layer need to do and how you want to implement the remote systems, and primarily 2 types of remote systems, supported systems and intermediary systems. And this distinction can be quite important, especially in the technical design, as well as how you reason about trust. In commercial systems, some of these may be mixed together as a commercial product, but I think even in that case, we should separate the 2 aspects of it. So it's really important we take them apart and understand which one you have trust dependency, which one you don't. All right, so that's it, and hope you enjoy this presentation. There will be more technical information that is available in IIW's online repository. If I can quickly go back there. Right here, so if you look for the 24th Internet Identity Workshop, has some of the minutes and notes, as well as a link to the slide information if you want to get hold of it. I will be making another similar presentation in September in Dublin for Linux Foundation's Open Source Summit. So that's next week. So hopefully I will share that presentation with you all as well. Thank you very much.